then
so
there you can go.
Yeah, so first I would like to acknowledge the people who have worked on the project, especially my former students and colleagues and all the collaborators throughout the world. And most especially the funding agencies who have supported us over the years. So, the incessant increase in the Earth temperature has caused the society to rethink about our energy systems. So there is a call for energy transition in which we agree that we need to increase the renewables in the mix. And the slide shows some of these renewable sources, but of importance for us today, it's solar. Why? Well, if you look at the estimated Earth consumption per year is around 16 terawatts. And there is a potential to harness around 23,000 terawatts of energy from the sun. So that means if you are able to do that, then there is no need for us to harness the energy from the other sources. So the question is, why haven't we been able to achieve that yet? And that is the topic of today's discussion. But before I begin delving into the details, I would like to show already that some of these technologies are being used. In Boulder, Colorado, where I'm currently residing, the solar panels are being used as building cladding. Also in the Netherlands, where I did my PhD, it rejoices. It comes as a joy when you hear that recently the Delft University have kind of upgraded their train station and make it fully solar powered. And then also, of course, I am from Ghana, so there is also the need to show a bit of this kind of technologies, how they are deployed. And here they are combined with hydro to power some of the remote communities in Ghana. And I must say that all those technologies are based on silicon, but of interest for us today is organic or solution process devices. And then today we'll focus more on polymer photovoltaics. Why? Because they are thought to be perfect for hot climate, and they possess a lot of nice properties. So we can tune their colors, they are flexible. They are also transparent, which means that they can be built integrated, which is really the future of this technology, where we can integrate them into various forms and for usage. However, these technologies face a lot of challenges, which I think can be classified, some of them can be classified into three. It's material dependent. The architecture of the devices in terms of module design is also something that we have to really consider, which is tough to do. And the process in itself, we know that most of these solution process devices technology cannot be done in ambient, so they are done in controlled environment. And there are also issue of toxicity, which is a bit debatable, but you can agree with me that some of the solvents and materials we use can become toxic. And when you talk about perovskite, lead is one of those materials that have been discussed. Moving on, one of the challenges is also known as the efficiency, how efficient these devices can be. As of today, I know this can be a matter of debate, but indulge me, I will lead you through when this technology started, especially with the bulk heterojunction solar cells in around 2000. It took us 2 decades to get to almost 20%. And on this chart, which is homemade, we pick the highest efficiency each year as we track them over the years to be able to make this. And here we have all the three technologies, the binary, the ternary system, and the tandem. And thus you can understand that there are a lot of effort that has been done in the community which have not made it on this chart just because they couldn't beat the yearly efficiency, which means you can imagine the enormous work that has been done in that direction to reach where we are now. Now, if we single out the ternary solar cells, which is the latest technology in the field, we started around 2009. We can also see the same trend over the years. If you compare that to the elephant in the room, because there's no need to, it's always difficult to talk about solution process technology without talking about perovskite. And this chart I borrowed from Dr. Asuo, who is my partner. And here you can see that the highest efficiency as certified by NREL from 2009 to current is around, is higher than 25%. And you can see that this trend has been, if you will draw a straight line, you can see it has been has been a very high slope. In that sense that while this is a good development for the community, it's also, it was a bad news for the photovoltaic field, the OPV field, because most of the attention was shifted from the organics to the perovskite. But thanks to the non-fullerene advent of the non-fullerene acceptors, the OPV field is still alive today. One other thing that we can talk about as a challenge is the manufacturing. We have a lot of companies who are at the forefront of the OPV technology, which means that the future is seen as depicted here, but obvious in this chart, in this image borrowed, that we like to see this technology integrated beautifully, not just to provide energy, but also in terms of decoration in our buildings, or mainly the malls or the stations and all other buildings that we can come across. Meaning manufacturing is essential to this development. And as we can see, for now, roll-to-roll and printing technologies, other printing technologies are at the forefront of that. So there's no real consensus in the community as of now. But as we can see, where we are now in terms of where we projected the future to be. Right now, we only have films, prototypes we can only make prototypes. And this example depicts a University of Newcastle in Australia, where they use this prototype on their roof to kind of harness energy. But the good news is that we are still projecting that this technology will take a share of the market in all the regions over the years, as projected here from 2021 to 2028. Which means that even though we have all these companies over the years, we couldn't reach where we are now, but there is hope for us to move ahead in terms of manufacturing. And as a summary, I like this graph a lot, which has been a publication done in the honor of Alan Higa, one of the forerunners of the bulk heterojunction technology. Here we can see that they have identified 5 core issues that will have to be addressed to be able to push this technology further, which is efficiency that we have already tackled, module design. Also, we have to look at flexible transparent electrode, especially when we want to do printing on flexible substrate. And most especially device stability, which is all reliability, whichever way you look at it. Some people use durability depending on whichever way you look at it. But one thing about the device stability is that it's a complex scope to look at, because it involves stresses such as photo-induced degradation, thermal degradation, and degradation due to moisture. And today's discussion will focus more on photostability, while we make some references to the other stability mechanism. We'll start first by looking at polymer fullerene solar cells, which is the beginning of the bulk heterojunction technology. In a sense that today we'll pay particular attention to the benzodithiophene polymers. Here, I would like you to pay particular attention to the side chain. Here we have the BDT, so the benzodithiophene is the BDT unit here, coupled with the TT unit. Later, I will show you what happens with the TT also. So this became the star class of polymers because they are made to be very compatible with 70 PCPM, which is a fullerene derivative. And when you make them into bulk heterojunction solar cells, you're able to achieve reasonable efficiency, which then was around 5 to 7%. Now, how do we move? Because the challenge is to increase this efficiency over time. So the chemists have been very supportive of the community, so they come with new ideas. So what they did is to replace this side chain by, especially the oxygen in the side chain, by a thiophene. And this gives a rather two-dimensional orientation of these materials in the thin film, which helps in transport and therefore enhances the current density. Now, we would like to look at this in two ways. First, from these polymers, which we may refer to as A polymer or the red polymer, anytime I say that, then you should know that this is the alkoxy side chain polymers on the BDT. And then the actinium side chain, we'll call them the blue polymer. So if you pay real much attention, the change is only happening. So this first one, the counterpart is B. So you can see the only change is on the side chain, and you can also compare these two also. And another strategy used by the community to increase efficiency is also the use of additives in the active layer. And one particular such additive is the dioxide, which has become popular in the field. So all this trick has been used to increase the efficiency. And when you move from the 1D to the 2D polymer, or the red polymer to the blue polymer in a blend with 70 ppm, you begin to approach 10%, which is a very good news for the community then. Now, as I said, we can look at these polymers in two ways. So if you look at the first polymers, which is something done, the trick played by Howe et al. In those days. If you look at the TT unit, so now we move from the BDT unit to the TT unit, you can see that they begin to play with a substitution. So here we have a kind of, you reduce your oxygen, and you get a ketone type of TT substituted polymer. And then when you fluorinate it, also you improve the molecular dynamics. So in that sense, they try to play with the VOC in the system when you combine it with 70 ppm. As you can see here, they've been able to achieve that by just playing with the substitution on the side chain of the TT. And we look at that also into details. In our case, we look at the 1D polymers, and as you play with them, you can see that the reduction or the removal of O help to increase the VOC from 0.6 to 0.7. And when you fluorinate it, you move to 0.76. And when you try to fluorinate directly the OO TT substituted, you move directly to 0.7, which helps in enhancing the VOC. The same thing for the 2D polymer. So now, while all these are good development for the field in terms of efficiency, the question then was, what does this do in terms of stability? And nobody has yet looked into that. So we decided to look at that. And what we did is to make devices and then expose them for a longer time under open circuit condition. And mostly we observe that the trend that we want to see, anything you want to see in the device can already be observed over 2 hours. So though we make this measurement over 8 hours, we decide to stop based on our limitation at 2 hours, where we already observe changes that we can really study into details. So we begin with the red and the blue polymer. And as you can see, truly we have increased the current density as we move from the red to the blue. And here you can see 2 more examples of that in terms of how it affects the efficiency. And then also if you consider the TT, playing with the TT, when you reduce the O, you improve the efficiency basically due to the improvement in VOC. And when you zoom in on the 2D polymers, you can really see that the change here when you move from the ET to the C and then to the TH. And of course, when you fluorinate also, it helps also increase the current density, so which are very good tricks for the community. Now, when we move to photostability, here what you can see is that though the change from the red polymer to the blue polymer was very great for efficiency, that is not the case for stability. You can see that you can observe a rapid degradation here under photo-induced stressor for these 2 classes. So you can see for the first red polymer and the counterpart blue polymer, and then also for the second red polymer and the counterpart blue polymer. And we try to look at this into details, looking at the other JV parameters. And clearly here you can see that what was the result, what causes this degradation is around the field factor. Mostly the JSE and the VOC experience similar degradation rates under the UV stressor. Then the question becomes, how do you know that this is due to the polymer? Because this is what we're trying to assume. And because also we assume that the 70 ppm, since these are from the same, the red and the blue polymer from the same family, will act in similar way. So the effect of 70 ppm should not be that much of a concern. So what we also try to do is to look at the interlayers, because the question can be, could this be due to the reaction of this polymer with the other interlayers such as P.PSS or the lithium fluoride if you are talking about conventional structure, or molybdenum oxide or zinc oxide. So we try to look at that, and what we tried various techniques. So first, what we did is to make devices without P.PSS, just on the bare ITO. As you can see, the efficiency reduces, but the trend still remains. Similar with P.PSS, which is known to be acidic in the community. So we try to use pH neutral P.PSS. And here you can also see that the trend still remains. And for the top contact, also we look at lithium fluoride, which we replace by calcium. And the top, the trend still remains. So here we can strongly say that the differences we see in the performance of the red and the blue polymer are solely due to the change in that side chain. Then we move on to look at the TT unit, because they also play some roles in terms of the VOC enhancement. And in that case, when you move from, when you reduce your aldehyde TT substituted into a ketone, you see that that results in an improvement of the slight improvement in the photostability. But then when you fluorinate, as we have already seen, fluorination exacerbates everything. So the photodegradation of photostability become worse. And then in the end, we'll conclude that it's better to do oxidant reduction than to do a fluorination, as you can see the huge difference in that. So in this case, we have contradictory results that some of the changes that we have observed in terms of the TT unit result both in improvement in efficiency and stability, but the other change results in improvement of efficiency, but is bad for device stability. So we look at light intensity dependent measurement, because that gives us an idea about what is happening in the system. And with the ideality factor, we can really how they progress over the exposure time. You can really see what is the charge dynamics in the system. And here clearly you can see that when we take the most stable, which is the ketone-based device, here we can see that the ideality factor did not change much over time. So it remained very constant. That could explain why the devices perform well under photo-induced stresses, which means that there is no increase of charge trap-assisted recombination in the system. As compared to the other ones, you can see that there is an increase. Well, this increase is not directly correlated to the amount of trap in the system, but at least it indicates that there's an increase in trap recombination in the system. We try to do the same thing also for the blue and the red polymer. And here we can clearly see that with each counterpart, the red polymer retain their ideality factor nicely over time, though it increased, but the blue polymers increases faster than the red polymer. So this leads us to the next techniques, which is the additives. And here we can see from literature, but well published in the past, that when you add additives in your pocket heterojunction active layer, you are able to influence the current density by increasing it, and therefore you also increase in performance. It's not just with DIO, but other additives we also use, such as chloronaphthalene or diodohexane. And here clearly also you can see that they all in different materials combination, they all improve the efficiency. Of course, in our case also, we decide to try that. And when you add it to it, truly the device is improved. So if you move from the red polymer, which are the closed circle curves, when you add DIO, which are the open circle curves, you can see that we have been able to improve the device current density and therefore improving the device efficiency. However, if you look at the stability, it seems DIO exacerbates everything. The degradation becomes more pronounced. And why is it so? What is so peculiar about DIO? So try to understand that. We also look at another additive, chloronaphthalene. And here clearly you can see that when you use chloronaphthalene, you are able to retain your device stability as it was without the additives. And also, of course, the efficiency are also similar or slightly improved. So there should be something peculiar about DIO which reacts with the light. So we try to understand that And what we did is to sieve the UV part of the solar simulator. And here clearly you can see from the initial curve, when you try to filter the UV part, you realize that your devices retain a very good level of stability. So therefore, the conclusion is that it's the UV part of the light that causes this degradation, which is not new because it's already known in the literature. But for us, in terms of DIO, that's the significant observation. So when you sieve or you filter the UV part of the light, also in the DIO devices, you can see that they also retain a very good level of stability. So therefore, there is a question mark between what happens between the DIO and the UV part of the light. And if you have good collaborators as chemists, they will propose to you to look at H1 NMR and mainly focusing on the monomers of this type of polymers. And what we did is to kind of have this monomer in solution and illuminate it over time. And here you can see the spectra from the initial position, and as we illuminate them every 10 minutes and we measured. And clearly here you can see that in the chemical shift between 4.8 here to, I mean, it's small, but you can just follow 4.8 to 6 ppm of the monomer. We have in the presence of DIO, we have appearance of new peaks after the initial, just after the initial exposure, starting from 10 minutes up to 120 minutes, with each peak increasing in intensity over time. And the peak around this kind of chemical shift, that's 4.8 to 6, belong to the vinyl proteins, which are known to be part of the alkenes. So therefore, these protons in the range of around the shift of 5.8 belong to the 7th or the 2nd hydrogen or proton on the alkene chain. And then when you move on to the chemical shift around 4.9, which also increase with intensity, that belong to the terminal vinyl protons that are labeled here HA and HB. Now, when you move to the aliphatic region, we also see appearance of new peaks around 0.89, which is observed to be a formation of an alkyl chain. So in that sense, there is it means that DIO goes under homolytic cleavage of the CI bond, giving you a hydrogen hydride, a hydrogen iodide, which is a strong acid, and then the rest are an alkyl chain. And this is what we see in this region particularly. And that means that DIO under illumination become a photoacid. And the chemists can give you a lot of drawing to tell you that all these reactions happen and there is ring opening, hydrogen elimination, and these are things that I do not fully understand. But of course, when you look at the facts, that shows that this happens. And all of these that I spoke about here, you don't really see them. You don't see these peaks when you only consider the monomer of the monomer alone. It's only appear when you add the DIO. So, and bring us to the summary of this part, we can see that the challenges we face for the polymer fullerene bulk heterogeneous solar cell is that they are purely material dependent. Whatever happens is always material dependent. The efficiency is low, the stability, we have a short lifetime of stability, and a lot also might depend on device engineering, which led to a group led by Christoph Prabeck to give ideas of how to design donors, as we have seen for the bulk heterogeneous solar cell, towards 10%, because the efficiency of these polymer fluorine were then limited around 10%. So the advent of the non-fluorine was good news for the community because it is they were counted to have facile synthesis route, which makes them cheaper compared to the fullerene derivative. They are known to have strong absorption, which means they will help enhance the efficiency a lot. They have tunable properties, so you can really play with them. And then they were thought or they were labeled to have enhanced stability. So what we try to do is to look at the workhorse material, which is ITIC, and compare it to what we already understand with 70 PCPM. And clearly here you can see that in inverted structure, the ITIC device perform less it was less stable than the 70 ppm. So we tried to understand this. And what we realize is that it loses a lot in terms of the fill factor. What would be the reason? Why would this be more advantageous in efficiency, but in terms of stability, photostability, that's not working? So we try to look at this from drift diffusion simulation done by Vincent in the audience today, which shows that the loss due to the fill factor is coming from the mobility, the changes in the mobility and charge imbalance in the system. So as you expose this for a longer time, you lose this much more in your mobility, and therefore your charges become imbalanced in the system. And this has also been an observation done by Abdulaziz et al., where they look at another system based on the ITIC and expose them for 10 hours, and then you can see that this effect is even more pronounced here. So what we did next is to look at the ITIC and its derivative. And what the chemist community also did is to play with the outer benzene ring by substituting them with CH3 and fluorine atoms. And clearly here we can see that in any case, fluorine is bad news for stability in terms of photo-induced degradation. And when you add a metal group, that improves slightly the photostability. Of course, if you do these changes in terms of efficiency, you gain a lot. Around the same time, Du et al. Also studied this same of material, but in addition, they studied the material with a double metal group on it and then a double fluorine group. And they also study an additional material where in the ITIC composition, the benzene rings here were replaced by a tyrosine ring. And in that sense, you can see their results. And they also prove that when you double the metal group, which becomes the worst performance here, you also lose a lot in terms of the fill factor. But one good thing is that with the 2F, you have a better stability. The fill factor does not change that much. And with their result, they're able to predict a 10-year lifetime for this type of device, PBDBT. So the same polymer combined with ITIC2F can give you a better result, which is also a good news compared to what we have done. But when you leave the realm of projection and you come to real experiment, you can see that shelf lifetime for the work done by Abdulaziz was kind of okay-ish, over 1,000 hours. But when you start exposing them to the sunlight, everything goes out of the window. But then when you see, so also showing that in this type of devices, the non-fullerene are not immune from the UV aspect of the degradation. So when you see the UV part of the light as shown here, you can also recover your photostability. And then also thermal stability has been shown to be also a problem for this type of devices. So what can we do to really help in this the technology? So the idea that came was, okay, if ITIC-based devices perform that well in terms of efficiency and they are degrading, why not try a ternary blend? So what we did is to keep this ratio, the ratio of the polymer and the ITIC, the ratio of the polymer constant, and then we increase the amount of 70 ppm in the blend with what we are losing from the ITIC. And you can see that this is a try and error problem. So what you have to do is to try a lot of ratios, and of those ratios, you will begin to see at what ratio you have the best result. And our best results are around these 3 ratios. And all 3 of them gave us the best efficiency and also the best stability. So we decided to stick with one of them. And here clearly you can see that ITIC has shown already a degrade over time, but when you start introducing your 70 ppm, you see a slight improvement in the device stability, whether in conventional or embedded structure. And that improvement is not only seen for stability, but it's also seen in the device efficiency, which are good news. So we have been able to do that, which is work that has been shown already in the past. But if you're able to really control the ratio of your ternary blend, you could have good devices. And to convince ourselves that this is not just a one-off result, we went back to one of our old friend polymers, which is the BDT-TT polymer. In this case, we combine with ITIC and 70 ppm. With the ITIC binary blend, you can see that the degradation was very much pronounced. But when you begin to play with 70 PCBM, introducing it and forming a ternary blend, you can see improvements both in efficiency and the device stability, which are good news. And that also led to us to really understand what is happening in the system. So we look at our collaborators who can do GWAS measurement for us. And here, when you look at the edge-on crystallite, we can see that the peak degraded rapidly. And when you look at the in-plane, the 010 in-plane peak around 15.4, this disappears rapidly after a few hours. And that shows that the similar observation have been made for the face-on crystallite, which also degrade for the ITIC devices, which also degrade rapidly over time, which means that they lose this system lose their crystallinity, and the molecular packing is being disturbed. And the good thing we observed that when you begin to introduce 70 PCBM, you are able to at least preserve this kind of crystallinity and packing over time, though it degrades, but it's not as pronounced as in the ITIT system. So if ternary blend is a good way to go, it also comes with challenges. You can agree with me that there are a myriad of opportunities out there because you have three materials instead of two, and you have to be able to make the right choice, and you have different configurations. So that brings a lot of challenges along the way. But these challenges has been discussed in this review, which most people, a lot of work that has been done has been captured there. But to only show you a few, you can see that Baran et al. Also show that in air and unencapsulated devices with different composition using P3HT and two other non-fullerene acceptors or molecule, you could have a good shelf lifetime in air compared to other binary systems. So it shows that ternary system could be a way to go. And then also under sunlight, in air, you can also, they have also showed that ternary blend outperform the rest. Zhang et al. Also show similar effect, but this is in control environment where ternary blend outperform the binary blend in under light stress. And then when you go to thermal degradation, also other groups, Chen et al. And Du et al. Also show that, of course, ternary blend can be a way to improve the thermal stability of these devices. And then this also has opened a lot of door for the ternary blend system for a lot of studies, which are nicely captured in this set of reviews. And reviews are a good way to capture all the work that has been done over the years. So in conclusion, we like to say that the OPV technology is dependent on a lot of things. And the fact that it depends on the materials and the chemistry it's a good news and a bad news for the community, because every material has its characteristics and can lead you to one direction or the other. And then also the device efficiency, which today can be questioned, but of course, because we are reaching 20%, but hasn't been the case over the years, that led to people trying to give rules where we can design material to reach a certain level of efficiency for the polymer fullerene bulk heterojunction system. And then also for the non-fullerene acceptors, it has been observed that they have an inherent efficiency limit. And then also in this publication in Nature by Federer Kerr and co-workers, they've also proposed ways to improve the efficiency in that device. Of course, we have the device stability and the printing technology also have to be looked at, and the module design. All of these are the challenges we are facing now, but the future is promising, and I hope that we could be able to put OPVs technology on the market very soon. Thank you for your attention.